Great. Okay. So just let me know if you cannot hear me well or if you have any question, just shout out. So let me start with a very big picture motivation about what my research is about and what I'm going to talk today. So these stained glass images of the universe show different ways in which you can observe the universe. One of them, the rightmost, is with light, with like optical terrestrial observatories and satellites. You can also see gravitational waves. And what we're going to talk about today is neutrinos, which is the leftmost panel. And what I try to do is to try to understand two distinct questions. And so the first question is, what does the universe look like in high energy neutrinos? And then the second question, which is going to be the core of this talk, is related to the origin of neutrino masses, and it's related to the question of can these high-energy astrophysical objects that we're discovering tell us anything about neutrino masses? And I like to show this picture because I hope the following thing happens. This is a image of the sun in neutrinos by Super Kamiokande. This is a fake color image, of course. But I'd like to bring this up just because, of course, some of the first signatures that we had for massive neutrinos were actually seen and retrospectively in the mismatch between expectations from solar neutrinos and data. So my hope is that when we look at the universe in high neutrinos and we see the sources, we will start finding discrepancies between expectations and observations. And of course, those discrepancies, much like the case of the sun, will require long discussion to see if what we're seeing is neutrino physics or is it astrophysics. And so it would probably be a long but very interesting debate. Okay, so with that in mind, as our goal, I have four stages that I want to talk about today. So the first two is going to be neutrino astrophysics and IceCube, and it's more like a recap just to have everybody on the same page about how do these detectors operate and what are the measurements that are relevant for the discussion that we're going to have later. And then the sort of main part of this talk is point three, where we're going to look for oscillations with these sources. And then point four, I'm just going to give some ideas of what are the next steps in this field, where are things going, and what are people thinking about. Okay, so let me just talk about neutrino astrophysics and the IceCube Neutrino Observatory. So the motivation to have IceCube and neutrino astronomy is to try to understand the origin of cosmic rays, and high-energy cosmic rays or cosmic rays expand a very large range in energy. So you see in this figure that they span many decades in energy from few GeVs all the way to 10 to 20 electron volts. And they have a very large variance in their intensity. And so the question is, how is the universe producing these extremely high energy cosmic rays and what are their sources? The highest energy cosmic ray was seen by FlyEye several decades ago, and it has 300,000, well, that many TVs in energy. And if you were to use conventional technologies to create such a particle, set as a particle, you will need to have an accelerator roughly the size of Mercury. And so I'm a particle physicist, so this is going to be my picture of how these objects that we don't quite understand and know operate. And so the idea is that there is some kind of accelerator, like in Earth, how we will do this. We'll accelerate protons with an accelerator, then those protons will like smash at targets and they will produce neutrinos. That's what we do, for example, at Fermilab and other similar neutrino beams. So we think that something similar may be happening in outer space where protons are being accelerated by perhaps a supermassive black hole, and then they are hitting radiation or gas around these acceleration regions that produce particles. So in particular, when you have proton interacting with light, they can produce neutrons and charged pions, or protons and neutral pions. And so you have production of neutrinos from the pions, charged pions, and the gamma rays from the neutral pions. And so that's the cartoon of these sources. So you could, of course, think about using the gamma rays to try to find these ultra high neutrino sources, but the problem is several folds. So in one direction, the ultra-high energy cosmic rays are bended by magnetic fields, so they don't point to their sources. And in the other direction, the high energy gamma rays that are produced by these sources can interact with the CMB per producing, making them no longer transparent in our universe. And so this is when neutrino enters. In a more sort of quantitative fashion, here I show you how we can see our universe. So here in the horizontal axis is the energy in electron volts, and the vertical axis is the distance of observation in megaparsecs. And everything that's transparent is something that you can see with light. And so you can see microwaves, optical, X-rays, gamma rays. And then when you get to this very high energy light, the very high energy light, as I was saying earlier, can interact with the CMB or other radiation in the universe per producing and no longer is transparent to our universe. And that is the terra incognita that is revealed by high energy neutrinos. Okay, so neutrinos, perhaps perfect messenger for these astrophysical sources. They are neutral, so they are non-deflected magnetic fields. They are essentially massless and absorb thermonuclear processes, but the downside is that they're also very difficult to detect. And so here enters the IceCube Neutrino Observatory. This is a picture of our computer facility down in the South Pole. So as you may know, the IceCube Neutrino Observatory is located in the geographic South Pole, and I just made these images to scale, so you can compare Australia more or less to the Antarctic continent. Antarctica is quite a large place, as is Australia. If you were to go there, our detector is pretty close to the geographical marker. This is a student I worked with that was over there a few years ago. So what is the detector we're going to use for these studies? So Antarctica has a rock as a continent, and then there's a glacier on top of it. And in the geographic South Pole, the glacier is about 2.5 kilometers tall. It's one of the most transparent and best quality in terms of optical properties and naturally occurring materials. The detector itself is actually buried within this glacier, and it's deployed between 1.5 kilometers and 2.5 kilometers deep in the glacier. And the reason it's deployed deep is because the quality of the ice is better in the lower part of the ice than the top parts of the ice. And it's made about detectors that are essentially photomultiplier tubes that can convert light into electric current. And they are deployed in these strings. So these are these vertical lines. And within each vertical lines, we have 60 sensors that are spaced out about 17 meters. These lines, or strings as we call them, are separated by about 125 meters. And altogether, it's about 1 cubic kilometer, which corresponds to about 1 gigaton material for neutrinos to interact. So it's the largest neutrino detector in terms of like instrumented volume. So the detection principle of the experiments is the Cherenkov light produced by charged particles made of neutrino interactions. So for example, when you have a high energy neutrino, it interacts in the ice or the rock and the detector, it makes high energy muon. And when I say high energy in this talk, I always mean things above 1 TeV in energy. And when you have a high energy muon, that muon typically is going to go several kilometers before it stops emitting Cherenkov light. And so the Cherenkov light is emitted with a particular light pattern, and by looking at the time of arrival of the light, we can actually infer the direction and energy of these events. And so this is a simulation that shows you one high energy muon that is transversing the IceCube array. So here, every dot is one of these sensors, these photomultiplier tubes. We call them DOMs for digital optical modules. And then in this talk, the color is always going to indicate time. So red in this place. So red is earlier time and blue is later times. And then what you're seeing here, if you look at this carefully, in the beginning of this muon track, you see that the light, which is represented by these lines, is emitting a cone-like shape. But then once the light travels, it starts scattering in the ice, and it has this sort of diffusive pattern that you're seeing here. So in the ice, the absorption length is much longer than the scattering length in the Antarctic ice. So typically, the scattering length is about 10 times smaller than the absorption length. So that means that a photon scatters about 10 times before, scatters significantly about 10 times before it gets absorbed. Okay, so that means that to reconstruct our properties, we have to know the ice properties very well to unfold them and obtain the true energy losses. So we can measure the direction of these events by looking at the time of arrival. Typically, these muon tracks are actually not contained within the detector volume because they are multiple kilometers long. But we can use the fact that at the highest energies that we are at, the muon energies are actually, the muon energy losses are proportional to the muon momenta. So we are in a regime where the muons are not minimally ionizing particles, but instead they lose energy in a stochastic fashion. So by figuring out first the track direction and then looking at the way the energy or the light is emitted within the trajectory, we can infer the energy. And the energy, unfortunately, due to the nature of the stochastic losses, is going to be always a very broad uncertainty. So these events are very big. If you ever visit Boston, this is one of the parks we have here, and you can see that this sort of events is a multi-city block kind of detector. We can see the neutrinos in various interaction types. So, for example, we can see muon neutrinos when they interact in the detector or around it. If the muon goes through IceCube, we can see electron neutrinos if they are interact inside or in the neighborhood of detectors, and then we can identify tau neutrinos as long as they interact within the instrumented volume at high energies. And so, how do we differentiate these different interactions is by the light, the morphology of the light that they produce. So muon neutrinos in the leftmost panel here produces very long tracks that allow you for a very good directional reconstruction. And so typically at the highest energies, much better than at a degree. Unfortunately, because typically the interaction vertex is not contained within the detector, and as well as the fact that the muon losses are stochastic, the N resolution is not known within a factor of 2. And so that's going to be important in the future. When I talk about tracks, I mean these sort of events that you see in the leftmost here. Then we have neutral current and electron-neutrino charge current interactions. Those produce hadronic and electromagnetic cascades. Hadronic and electromagnetic cascades currently cannot be differentiated within IceCube, so we cannot tell if it was a neutral current or an electron-neutrino charge current interaction, except for very specific cases. And they produce these approximately isotropic light emissions, so we call these cascades. We can measure the energy calorimetrically for 15% resolution, but now the direction is much more challenging because we don't have this long lever arm anymore. So that's a order tens of degrees. And then finally, we have tau neutrinos. This is my favorite neutrino type, and those we can identify in IceCube on an event-by-event basis. It's one of the few observatories or detectors that can do this right now. So here what is going on is you have a tau neutrino that's traveling along. It interacts in this red blob location, makes a very boosted tau. The tau goes a bit more and it decays in the green slot, making a small splash of light. To give a sense of scale, if you have a 1 PeV tau, that will go typically about 50 meters before it decays. Okay, so that's how we see different flavors and so first order reconstruct these events. So that's what I want to tell you about IceCube. Those are the pieces that we need to talk here. And now I need to tell you a little bit about what are the sources that we're going to use to do the physics that we're interested in. And so one of the big challenges in these sort of experiments is that even though the detector has a 1.5 kilometer overburden of ice, there is still a lot of high energy muons that are producing cosmic air showers that manage to reach our detector. So what you're seeing here in this video is what happens is a simulation of 10 milliseconds of IceCube data. And so we see about 3,000 muons from the atmosphere per second. So it's going to be 10 to the 11 per year. Then we see atmospheric neutrino one every about 6 minutes. And then that's going to give us on order of hundreds of thousands of atmospheric neutrinos per year. And then we see cosmic, so astrophysical neutrinos on the orders of hundreds per year. So the statistics that we're going to work with is going to be relatively small, and we have these very large backgrounds that we have to subtract. So measuring the astrophysical neutrino flux has been very challenging, and the reason is that the astrophysical neutrino flux is very small compared to the large atmospheric neutrino and muon backgrounds. And so you can see this represented in this figure on the right, where the horizontal axis is the log of the energy of the neutrino, and the vertical axis is the flux scale by energy squared. So typical sizes of astrophysical flux are at the level of this green bar over here. And you can compare that to the size of atmospheric neutrino emission, which are represented here for electron and muon neutrinos as these red and blue crosses. And so you can see that the background is much larger. And remember that per every atmospheric neutrino that we see, there is a million muons that we have to take over. So how do we actually see astrophysical neutrinos? Well, one way is to look through the planet. If you look through the Earth, the high energy muons cannot go through such a large amount of matter. So you're only left with the atmospheric neutrino background. However, you no longer can see the southern hemisphere if you do this. And so to see astrophysical neutrinos, what we do is we model the atmospheric neutrino background as a function of energy. Which is in this figure on the right is the purple line. That's the model of the atmospheric neutrino flux. And then we see the deviation of that model versus a function of energy. So you can see that at high energies, the data overshoots the prediction for atmospheric neutrinos, and that is how we identify that these are astrophysical neutrinos in nature. The other possibility is to, instead of using the Earth as a beta for muons, to use the outer layers of the detector to be able to reject these large muon backgrounds. And so the strategy here is to only look at events that interact within the instrumented volume. So the advantage here is that now we can see the southern hemisphere, but our detector is now much smaller because we have sacrificed all of this outer layer. So that's the downside. So that means that IceCube is very efficient to see the northern hemisphere, but when we talk about southern hemisphere, our detector is effectively smaller. So I like to show this figure because it's how astrophysical neutrinos were first discovered. So this is the distribution of events, of the high energy events that interact within the detector instrumented volume. And so you see here is three-dimensional histogram. The left figures shows you the charge in photoelectrons that the events deposited within the detector volume. The right axis shows you the amount of charge in the outer layers of the detector. And the vertical axis is just rate. So what you're looking for is things that enter your detector, do not leave any charge outside, so that means they're not atmospheric in nature, and then leave a lot of energy within the array. And so if you look at this distribution, there is this line that sticks out in the low charge, and those are actually the astrophysical neutrinos. And so these are some of the highest energy neutrinos ever observed. So the first one, seen about 10 years ago, were named by Muppets. We no longer name them because now we have many of them, but they have these ones here. Again, the event displays, the colors indicate time, and the energies are about a few PeVs. Okay, so we use these techniques to try to measure the physical neutrino flux. So what we're going to need in this talk is summarized in the following slides. So here I show you what we know so far of astrophysical neutrinos. The horizontal axis is the energy of the neutrino, and the vertical axis again is the intensity. And so these red crosses are measurements of astrophysical neutrinos of electron and tau flavor. Those are cascade measurements. And then this black bar or gray bar that you see here is measurements using track events. So those represent the all-sky neutrino emission inferred by IceCube data. Okay, most of these neutrinos are actually not associated to any particular source, so they have unidentified neutrino sources. So something interesting that happened now a few years ago is this in 2017 event that was a high energy track. Again, this is going from left to right. It's a high energy muon that is going through a detector. And this was interesting because there was a correlation seen in Fermi on the flaring blazar in the neighborhood of these events, and later also observation by MAGIC. And so this led to the publication of this first neutrino source, which is known as TXS 0506 plus 056, and it was published on Science several years ago. And so this is now we think this is a transient source. So why do we say that? And so we looked in the direction of TXS and looked for the neutrino emission as a function of time. So what you see here in this top figure is the significance of events of expected background in the direction of TXS. So the larger means that there is a significant excess over background, and zero means there is compatible with background. And so you see that there are two, just focus on the, there are two types of analysis, but that's a technical detail. Let's focus on the orange Gaussian analysis. There are two spikes in this distribution, one of them in 2017, and then a larger one in 2015. So 2017 is the one that has this gamma ray correlation, but when we investigate this direction, we find this larger flare in late 2014 that has about 30 neutrinos associated to it. However, this larger flare was actually not seen in gamma rays at the time of this larger emission. Another thing that's interesting, if you look at some of the highest energy neutrinos we have seen, you can study the time of arrival of these neutrinos and gamma ray observations in those directions. And so here I show you three of these high energy events, and the purple line corresponds to the time of arrival of the neutrino at the IceCube array, and the black or blue measurements are gamma ray measurements. So the leftmost is Fermi, LAT, MAGIC, and then Fermi LAT again. And so you can see that it seems that, at least for some of these events, the neutrino emission and the gamma ray emission is not fully correlated. So something complicated seems to be going on at these neutrino sources. So we have also looked at the neutrino sky and just asked the question of like, okay, so if I look at all the sky, what is the brightest point, the largest excess over background? And that happens to be in the direction of the galaxy NGC 1068, which is a safer galaxy. And in that case, we see a very significant emission. And so you can see this on the right, the background on top of the events. And this is the brightest state neutrino source that we've seen in the sky. We can also look at the gamma ray emission and the neutrino emission from NGC 1068. This is shown in the figure here on the right. So the horizontal axis is the energy of the gamma rays of the neutrino. The vertical axis is the intensity. And the green bar corresponds to the neutrino flux. And then the black and blue are upper limits on the gamma ray emission. And so you can see that the gamma rays are much lower than the neutrino emission. And one possibility to explain this is that the gamma rays are getting attenuated at the source because of the shorter interaction length. Okay. So that means that we have a couple of sources. So here are the fluxes that correspond to these objects. But still, most of these diffuse spectra is still unassociated. The other thing that has happened a couple of years ago now is the observation of our galaxy neutrino. And so here you see different pictures of our galaxy. The top one is our galaxy in optical light. The B panel is in gamma ray. And then you can fit the different components that produce the gamma ray emission and obtain the component that corresponds to pi naught production. And that is shown in the panel C. Now, the galaxy for us is mostly contained in the southern hemisphere for IceCube. So as I was saying earlier, when you have look in the southern hemisphere for IceCube, that means our detector is effectively smaller, and it typically cannot use muons as the detection method because of the large backgrounds. And so the typical uncertainty in our angular resolution for the southern hemisphere for cascade-like events is shown as a circle here in the panel D. And what you have to do is you have to smear out the distribution in C to get D. And so that's what we expect to see in the galaxy. And the bottom one is the data observation. So I should say that this was a first analysis that we did. And what we will show this summer at ICRC and other conferences are going to be very detailed studies of the different parts of the galaxy that are yet not public, but will be made public this summer. So what does that look like in our big picture here? So we have these two sources, NGC 1068 and TXS, and then we have these galactic neutrinos. The galactic neutrinos are about 10% of the all sky emission in these lower energies. Have been, discovered high significance. Still, most of the neutrinos are unassociated, and we will go back to this point later. But that's what we have to work with. We have this all sky unidentified emission, we have these galactic neutrinos, and we have a couple of sources. And then we're going to do some particle physics with these objects. Okay, so now I'm going to go to the core of what I want to talk here. So of course, the question is, how do particles acquire their mass? Like in the standard model, the fermions acquire their mass by interacting with Higgs. We do not know if that's the case for the neutrino. The neutrino does not have a right-handed neutrino. And so the question is, if where is the right-handed neutrino, if that is the way the neutrinos are acquiring their masses. There are all possibilities, but that is one option. And so what are the options of the neutrino mass? And this is a very schematic way of thinking about it. But we know the neutrino mass is much smaller than the mass of the other electrons and other fermions. So we think that there may be something different or special going on with the neutrinos. So people typically think about neutrino masses in two ways. So one way is to think that they are Majorana fermions, and the other one is that they are Dirac like particles. And I just want to point out these papers here on the left because these are some interesting, relatively recent arguments from string theory models that motivate Dirac-like neutrinos. And so if neutrinos are Majorana particles, the way you could prove that is by looking for neutrinos like beta decay, which is this process where the nucleus decays before the neutrino emissions. And there is a very broad experimental program looking for this sort of signature. Now, let's put ourselves in the other situation. So what happens if the neutrino mass predominantly is due to a interaction mass like the electrons with a right-handed neutrino and the Higgs on a small Yukawa-like thing? Well, if neutrinos are exactly Dirac, we will define what that actually means in a second with more detail. Then one thing that you could do in principle is you could measure neutrino beta decay and then maybe not see it. You will not see that process. You could infer the neutrino mass from direct neutrino measurements and cosmology. And then if you are in the inverted ordering, you could actually then conclude it's not Majorana. If you're in the normal ordering, unfortunately, there is this parameter space that goes infinitely low. So you will have to then argue that you are not in that so-called funnel in the normal ordering to say that they are Dirac particles. Now, there is this other possibility that neutrinos are quasi-Dirac particles, so they're a combination of these two things. And as we will see in a minute, that's going to produce ultra-long baseline oscillations, and that's where we actually are interested in looking for. And so the neutrino mass, if we have a right-handed neutrino in the picture, is going to be summarized by this operator that has this matrix. And so this matrix has these off-diagonal terms, which corresponds to the Dirac-like contributions to the neutrino mass. And then it has this term here, which is this MR term, which is the mass term associated with the right-handed neutrino, which, since the right-handed neutrino is a singlet-stand model, in principle is a free parameter of the theory. Now, this term here is going to produce lepton number. It's a lepton number breaking operator. And so if we say neutrinos are Dirac, we typically mean that this MR term is exactly 0. People also talk about the seesaw scenario where this MR term is very large and it makes the effective mass of neutrinos very small. And the case we're going to talk about today is the so-called quasi-Dirac scenario where this MR term is very, very small compared to MD. Okay. So what happens in this case? So in this case, what happens is you have your neutrino mass states, nu1, nu2, and nu3, but there is a small right-handed neutrino mass, which what does, it produces small mass splitting between your essentially left and right-handed neutrino states. And so what that sort of makes is like it introduces some kind of hyperfine splitting in the neutrino mass spectrum, and that mass difference between these mass states is going to depend on this right-handed neutrino mass exact value. So how large is this mass difference? Well, if you look at constraints from solar experiments, it cannot be larger than 10 to the minus 12 electron volt squares. And if you take models where this MR term is coming from lepton number breaking that is broken at the Planck scale, you end up getting theories that claim that this delta M square can be as small as 10 to the minus 22 electron volt squares. So that is the range of interest. The rightmost, the largest, is sort of the limits from experiments, and the leftmost is from arguments of making this lepton number at very high scales and some model building. So what does this mean experimentally? So experimentally, what this is going to cause is these long baseline oscillations. So these mass square difference are very different than our known mass core differences. And so the oscillations that are relevant, in this case, are always going to average out the known oscillation frequencies, which are very fast compared to this very, very slow oscillation frequency. So for example, if we have NGC 1068, whose distance is about 14 megaparsecs from us, and I pick a mass core difference of, for example, 10 to the minus 17 and a few, I can get now oscillations between my states. But unlike my normal oscillations that are just mixing my flavors, these are oscillations between left and right-handed neutrino states. And so that means that when the oscillation goes to a right-handed neutrino state, now it's completely invisible. So what I should see here is the disappearance of my active neutrino flavors as a function of energy from this source. Okay. So the idea would be to observe multiple of these sources. And for each source, we have the distance to the source, and we could measure the energy distribution from the source. And so if there is an oscillation scale that is fixed by this delta m squared, then sources that share the same distance to energy ratio should have the disappearance of neutrinos at the same L/E. And I think this is a very strong signature. I mean, I don't think there's any reason why objects that are producing neutrinos with different mechanisms, that are different distances, but later you combine them in such a way that the ratio of lengths to energies are preserved, will have the disappearance of neutrinos in a correlated way. So this is a very powerful signature as long as you have enough sources. So I'm going to talk about this in a minute. So what are the relevant oscillation scales? So this is a figure from a paper that's coming out from my student, Kiera Carloni and Miller McDonald. So what you're seeing here on the left is the neutrino rates from natural neutrino sources per kiloton year detector. Okay. And the horizontal axis that you see here is the L/E that corresponds to that flux. And what you see below is the mass square difference associated with that L/E. So for example, and there are two lines here, so there's two horizontal lines here that tell you the kiloton year of super K and IceCube to give a sense of scale. So things that are above that line should produce events within those detectors, and below that lines do not produce events within those detectors. So of course, Super Kamiokande they can see solar neutrinos and they can see atmospheric neutrinos, and through their measurements you can know the atmospheric mass square difference. The IceCube can see not only those. Well, we cannot see really solar. We cannot disentangle solar neutrinos from our background, but we definitely see atmospheric neutrinos. We are looking for atmospheric neutrinos from the sun. We can talk about it later. We can see galactic neutrinos and some of the source neutrinos. And so you can see that when we look at these faraway objects, those are going to correspond to smaller values of this mass square difference. And the question is there a mass scale to the right of, I'm sorry, and the orange arrow here corresponds to the limit from solar experiments that constrains up to about 10 to the minus 11 or 12, depending on the analysis. So the question is, are there any hyperfine splittings to the right of this mode? And so we have three astrophysical sources that we can use, the point sources, galactic sources, and the diffuse. So if we look at a single source, what we can look is the distortion of the spectrum of the source. So what is shown here on the left is the expected number of events in an IceCube detector for a model for the NGC 1068, as shown as a black line. And then when you put the oscillations, what you get is this histogram here, which is very different from the original source prediction. However, there are uncertainties in the astrophysical models that produce sources. So once you try to tweak these models parameters to reduce this effect, you get something like this purple line over there. So the end resolution is going to be critical to see this. So I show you here in the plot on the right, the sensitivity to this mass core difference from the sources, and we're talking about mass core difference of 10 to the minus 18 electron volt squares. And on the left, I show you the distributions of shapes, and again, black is standard model-like, and the other colors are these oscillations. And you can see the top is if you have 10% in the resolution, and the bottom if you have 50% in the resolutions. The reality is that in IceCube we have somewhere around the 30% in resolution for some of our best events. And so if we were to improve in that, we could really get a lot. This is done by Kiara and Ivan. With this analysis that we study the sensitivity of IceCube and then IceCube projection to this signature. So the top figure shows you the significance as a function of the mass square difference. For the sources that are more significant, so this NGC and TXS, I didn't take about this PKS source, but these are the most significant sources. And unfortunately, it's not very good. You can barely get to 2 sigma. And the reason is that, the statistics is small and you don't know the fluxes very well. However, if you were to find more sources, here are some source candidates in the bottom, then you could do this thing that I was saying earlier, where you could correlate the different neutrino sources from different objects. And that is very powerful and is no longer that affected by systematic uncertainties. So if you can do that, then you can get very, very high sensitivity to this physics. The other thing is the galaxy. So we are in our galaxy, we have little rotating neutrinos. So then galactic neutrinos are distributed in our galaxy. And the way they're produced, according to what we see in our latest measurements, it's compatible with production from diffuse emission of neutrinos. That means that are produced, it seems they're compatible with the production of galactic cosmic rays hitting gas in our galaxy. So here on the left, I show you a model of galactic cosmic rays in our galaxy. The middle panel is a model of the gas distribution in our galaxy. And then what you do is you multiply these two together, and then you end up with the distribution of neutrinos within our galaxy. And so then what you can do is look for oscillations in these scales. So in this, we did a very simple analysis where we divide the galaxy in these pieces for the inner part, the outer pair, and the high latitude and low latitude. And then you can see that if you divide in different pieces, there is a decent distribution that is different for each of these pieces, which causes an oscillation probability that is distinct per each of these distributions. And here what you can see is the effect on the expected effect in like IceCube and another experiment called ChemtraNet. And so the solid lines are the standard model like prediction for the model that we have, and the dashed lines are when you have these oscillations. The bad news is that when you put everything together, you get this mass square difference that is, well, you're exploring new parameter space. Unfortunately, the sensitivity is also not that great. And the reason is that there is uncertainties in this galactic neutrino emission, and the statistics is also not great. So what we need to do here, if we want to get this better, is to get more neutrinos and improve these galactic models. Okay, so then, well, it sounds like we are in a little of a trouble because the sources, galactic or galactic sources, are very statistically limited. We don't have enough of these events. But if we look back at this figure, we see that most of the neutrinos we see are actually unassociated neutrinos. So could we do something with these diffuse unassociated neutrinos? And this is discussed in this recent paper by Kiara and company. And so what we did was a first analysis on this, where we assume that the neutrino emission of the universe follows the star formation rate. So here you have the star formation rate, a function of redshift. And that implies that there is a distance distribution in terms of redshift for these neutrinos. So what we can do then is convolve it with an oscillation probability of 10 to the minus 19, which is going to be a gigaparsec scale oscillation length. And that's going to give us an oscillation spectrum. And because the oscillation length is so large, even though you have these two different models for the star formation rate, it turns out that you get very similar oscillation line features in the end, shown by the difference between the solid and dashed lines. And so we did an analysis where we looked at the IceCube data, which is separated into cascade-like measurements in orange and track-like measurements in red. And the data points are shown here on the left, where the horizontal axis is the reconstructed neutrino energy, and the vertical axis is the emission. And you can see again the IceCube measurements here. So our standard sort of baseline approach is that they follow a power law distribution, which is shown as the black line. And so then we put an oscillations according to this spatial distribution, and that gives us this shape here. And because there is a small tension at the low energies between the cascade measurements and the track measurements, it makes a little of a shoulder. It turns out that when you do analysis about, delta chi-square of about 8 units. So then we can see what that means in terms of this mass square difference. And so the left figure here shows you the mass square difference, again, in electron volt squares. And the vertical axis is the test statistic. So you can see various lines here. So the yellow line is some size of from neutrino from supernova 1987A. And then the red line is our delta chi-square. And so there is a region in the is red band that is very disfavored. And that region is very disfavored because, I'm just going to flip back to the previous slide, because in the inner range between more or less 10 to the 4 and 10 to the 5 GeVs, the data is very packed together. So if you try to put an oscillation there, the data really doesn't like you to do that. And so that is why this region is disfavored. And there is a small preference for a delta M square of about 10 to minus 19. And that comes from these features at the low energy part of the spectrum that are driving that significance. We also did a study where we have two different delta M squares. That has additional effects, but it doesn't really give you a very different shape. It's mostly driven by this spectral distortion at low energies. So I will just leave that there. Okay, so that's the physics that I've been interested in doing, this sort of very long baseline oscillation. So let me just, in the few last minutes I have, talk about, how could we try to resolve this and get more information? So the bigger question is, where are these neutrinos coming from? Like, if we were to be able to identify these neutrino sources and measure more sources, then we could, do this thing I was saying earlier, where we could look at the correlated neutrino disappearance across these astrophysical objects, and we could do lots of really fun things. But the problem is, we do not know where these neutrinos are coming from, and so we can only do simple ansatz. So how do we solve this problem? Well, we need more neutrino telescopes, and that's something that our community has been working on very hard over the last years. So here in this illustration, I show you various neutrino telescopes. So the ones that are blue labels are currently constructed or under construction. And those are the Majorana Observatory, very high energy neutrino detector, IceCube in the South Pole, Net in the Mediterranean Sea, and then Baikal GVD in Russia. Then you see all of these white labeled detectors. These are all proposed experiments that use different technologies, and the technologies are labeled as well. There are radio detectors, there are Cherenkov detectors, there's particle detectors, kind of like Oyer, and there are ideas for water Cherenkovs. In particular, China has had is doing a very strong push towards a large volume detector. And of course, we have a proposed expansion of IceCube in the South Pole. So you see that the community is really trying to expand in multiple directions and multiple technologies. So first, let me tell you what will happen with IceCube. So we have an IceCube upgrade that's going to put 7 new strings within the IceCube inner piece that's been funded and will be deployed in 2025. So that means it's December. And I'm very excited for it to happen. One of the great things we're going to do with this upgrade is we're going to really look very carefully. We have lots of calibration devices to look very carefully at the ice properties. That's going to improve all the reconstruction of our archival data and flavor identification. So what does it mean for low energy physics? It's like currently, if we have a low energy neutrino event at 4 GeVs, it looks like in the left, in the deep core, which is an innermost part of IceCube. And then this is how we look in the upgrades. And this is really good. It's not particularly useful for astrophysics, but for things like atmospheric neutrino oscillations, it's a really big game changer. Later, we hope to build IceCube second generation or IceCube Gen 2. And so that's supposed to be about 10 times larger detector than IceCube. And it's going to use next generation modules that, unlike the original IceCube that had a single photomultiplier tube per detector, this is going to have multiple of these detectors. And then, by the way, this will be deploying our IceCube upgrade, which we are putting out this December. And so we're going to test these detectors now and then put them in the, hopefully, Gen 2. Then I just want to talk between the difference between water and ice neutrino telescopes. So in ice, in the Antarctic ice, the absorption length is longer than the scattering length, which means that there is lots of light, but the light gets smeared out. So you can see that on the left. Now, if in water, the scattering length is shorter than the absorption length, so the light is diminished, so it's dimmer. However, there is less scattering, so it goes in straight directions. And that's what you're seeing here on the right. The density of photons is much lower. However, the photons are now going all in direct location, which is very good when you're trying to figure out where things are coming from. So water detectors, you need to have tighter instrumentation because there's less light, but you get better particle identification. And so the largest water-based neutrino telescope is CAME2NET, being deployed in the Mediterranean as we speak. So right now, this is every one of these things has 18 of these domes, and they put them in these big wheels that then they drop them in the water, and then it unfolds automatically and makes these beautiful strings. The detector of the high energy detector is called ARGA, and it will be deployed close to Sicily, and it will be eventually made of two building blocks, which will be a gigaton scale experiment. This is an event that they saw a couple of years ago, but reported this year. And this is a simulation of a very high energy mu neutrino that goes through the array. Here, the little spheres are telling you the photons that are observed, what detected by the different photomultipliers. And unlike the IceCube picture, because the detector have multiple PMTs, you're seeing all of these directions. So these events really light up their whole array. This was published in Nature earlier this year, and this muon has been identified to have at least an energy of 120 PeVs, which is a 100 PeV neutrino observation. So, well, what does that mean? So here in the horizontal axis is the neutrino energy and the intensity again in the vertical. And in the left, you see these IceCube measurements, and then there is this cross here for the CAME2NET bands. And I show you two different crosses because they have different interpretations. So if the CAME2NET event is due to a point source, then maybe it's a parameter in a direction where IceCube was not very good at observing it. So the inferred flux is larger. If the event is due to a cosmological neutrino flux, so this means it's an isotropic neutrino emission coming from cosmic rays inside of the CMB, then the most likely flux of these events has to take into account the non-observation of IceCube and other detectors of ultra-high energy cosmic rays. And so the blue one corresponds to the assumption of cosmological neutrino emission, and the other one is only if CAME2NET observes this particular event. So one thing that we did with this was kind of fun because one thing that you can do is constrain, for example, how superluminical a neutrino could be. If the neutrino is superluminical, it could emit vacuum Cherenkov radiation, and the observation of this very high energy neutrino constrains this better than any other prior measurements at the level of 10 to the minus 22 parts. Okay, so that's great, but what's the issue of finding sources now? As I was saying, when you look for a source, you have to scan the whole sky and look for the bright spots. So if you were to do that, it turns out that given our resolution, that is going to constitute about 400,000 trials as you look at every pixel within the sky. So the p-value of the highest p-value source, if you were to do a scan, is about 5.3 sigma local p-value. But once you account for the trial factors, you get a 2 sigma p-value. So when I tell you, oh, we have seen NGC 1068 or TXS, how is this possible if we're talking about 4 sigma events if you have these rush trials? Well, the issue is that if your astronomer colleague tells you these are the good sources, don't look at everywhere in the sky, then your trial factor is much lower. And then you can find objects like NGC 1068 and whatnot. So if you know where to look, the various sources are currently detectable. And so this made me think about Earth-scheme neutrino detectors. And so why am I saying this? Because an Earth-scheme neutrino detector is only sensitive to tau neutrinos, which means that tau neutrinos can only, at high energies, can only be produced significantly from astrophysical objects through oscillations. So when you have a tau neutrino that comes along, it interacts in the mountain, it makes a tau that decays and makes a shower. And so in these sort of detectors, like the Pierre, for example, geometry is key for acceptance of neutrino detection. So of course, you would like to have a bigger mountain so you can have a better acceptance. Maybe have your mountain top of your detector so you can see all over the sky, but of course, you cannot do that. So the next big thing you can do is do this idea which we call TAMBO, the Tau Earth-Summer Mountain-Based Observatory. And the idea is to have a mountain that has a V shape, and the neutrino interacts in one side of the mountain, and then it produces a tau that disintegrates in between the mountains and makes a shower of particles that then you try to look in with a detector, right? And that has been looked at with many of my students and postdocs. And so we actually went to one of the sites we were looking into. Peru, we have a bunch of sites, but one of them was in Peru. There's a big valley in the Andes called the Colca Valley. That this actually picture doesn't make justice to it, but this is about 4 or 5 kilometers wide and several kilometers deep, where you could have the neutrino interaction. We're trying to look for some prototype locations for the detectors. And so how that looks in the simulation, you have a neutrino coming on. It, as I was saying, it disintegrates, makes some of showers, you see on the left. And then if you have an array of detectors in the mountain, you can see the shower deploying. You can reconstruct the direction and infer it. So what's the acceptance of this? So if you were to put 5,000 modules in the mountain, so that's something, these modules are relatively scintillator panels, then your effective area in the tens of TeV energy range is actually larger than IceCube for, we think, a fraction of the cost. So that is the sensitivity we currently have to astrophysical neutrinos is shown here. So the blue line is IceCube measurements. What we call time Vito is like our sort of test array of 100 of these panels. And then this solid dashed line is if we had 5,000 of these modules in a mountain, and then we could do really good physics. So we expect to have, with 5,000 sensors, about order 1 event per year, given IceCube observations. But the good thing about this is that every event that we see is a tau neutrino, so it has to be astrophysical, and it will have a very good angular resolution, better than 0.5 degrees, given the array configuration. So that means that if we see a tau neutrino here, we can tell IceCube to look in that direction, and then this will significantly reduce the trial factor once they're looking at the sky. Okay, so neutrino astronomy is a growing field. This here represents the volume of neutrino telescopes as a function of time. And you can see that we start with 1 cubic kilometer, and now we're trying to build these experiments, ChemTenet and Baikal, and that's going to grow our volume to about 5 cubic kilometers. And then there are many ideas in the next generation, and they add up to a very large volume. Hopefully, they also become realized in the end. It's not only about building more detectors, it's also about detector specialization. So here what I show you is as a function of energy, the different components we're trying to measure: atmospheric, galactic, extragalactic, and ultra-high energy neutrinos. And depending what you're trying to measure, there are different technologies that are a little more advantageous, like water detectors are very good in the resolution, so they can suppress the atmospheric background very effectively. They're very good at galactic neutrino searches. IceCube is very good in this intermediate energy range. And then these mountain observatories are very cost efficient in the energy range here. And then higher energy radio detectors are much more efficient than later. And that's it. So I think we live in very exciting times, particular astrophysics, with the first neutrino source appearing, seeing all these neutrino flavors, and starting to do these ultra-long baseline neutrino oscillations, where we can look at these very, very tiny effects. And this is the opportunity to discover new oscillation scales of astrophysical neutrinos. There is some now constraints on the data and some hints. And there's still lots of IceCube data to analyze. We have an upgrade coming along, and there is more neutrino telescopes on their way, which means more data. So I hope we find BSM physics very soon. And thank you on behalf of my group and my team.
Thank you. Do we have questions? Those of you who are online who would like to ask the questions, just speak out, because I can't really see you.
Yeah, can I? I'll start. Can I ask about the various neutrino fluxes you were showing? I mean, what like for example, the plot where you had a few of the extragalactic sources and then the galactic flux. Yeah.
This one.
So at some point, the galactic flux gives way to the extragalactic flux. Is this? And then in your final slide, you sort of had this point at which they cross over. Is this crossover sort of detected? Like, do you know the point at which the extragalactic flux starts to dominate, and like does your galactic study, like if you take like low galactic latitudes compared to the high galactic latitudes, do you see this where you get this crossovers?
Yeah, so this, yes, to be clear, in this slide, this is these energy ranges and values are kind of like for illustration, they are not exact. We have not quite measured that crossover. And one thing that's interesting is that the galaxy is typically much, if you look at the whole neutrino emission from the sky and compare it to the galaxy is much dimmer than the extragalactic neutrino emission, which is not what you see in light. but we are not sure where that crossover is. I mean, where is this figure line? Where is that? I think the data here. So if you look at these extragalactic neutrino measurements, this was in yellow. There is some data points that suggest that if you look at the yellow ones, for example, that it's going to turn downwards eventually. And so the crossover, if it does, is somewhere probably below 10 TeV in energy. We have a fairly good understanding of the spectral index that we expect from galactic neutrinos if they're produced from cosmic ray collisions. So we know how this line, the purple line, extrapolates to left energy. But yeah, we haven't quite established that crossover point. It probably happens somewhere below this 10 to the 4 GeVs, but that has not been established yet.
And the various sort of sources within the galaxy that you mentioned, this is not out yet, right? But would these also have fluxes which are around that level? I mean, like to what extent is that galactic flux sort of contributed by a few kind of key sources within the galaxy versus like the whole galaxy?
Yeah, that's a very good question. And so the measurements of the galaxy, where we use a template based on the pi zero map, if we try to fit that, the flux that we obtain is very compatible with the calculations of just having diffuse neutrinos produced from cosmic ray collisions. However, the normalization of that flux has a large error, which depends on the amount of gas that actually exists within our galaxy. And so there are models where you could explain the whole flux that we see from the galaxy from cosmic ray collisions with gas. And there are cases where you are actually below the prediction, and that, of course, implies that there are sources. We do not know what is the current situation given the uncertainties in the normalization of the cosmic ray of the galactic neutrinos produced by cosmic ray collisions.
Mm.
So the answer to your question is we do not know.
Yeah.
But
So your
yeah.
quasi-Dirac case, you were considering the whole galaxy, right? It was.
Yeah, so we consider the whole galaxy, and one of the reasons that we have relatively poor sensitivity is because we have to consider, we have to consider the uncertainties in the gas distribution. So here I show you some examples of models of gas distributions that are out there in the markets. Also, you can see that they look quite different, right? And so when you put these uncertainties in, both the normalization of the whole flux, which depends on the study density, and the spatial distribution is quite uncertain. So that's what smears out that's why the galactic neutrinos don't quite reach this like 5 sigma level. This is because we don't understand this emission as well as we could. And this is, I think, due to our sort of limited understanding of the gas distribution in our galaxy and whatnot. And of course, yeah, I guess that's the point.
But there's last thing is I just remember when I was reading that galactic IceCube paper. I mean, there were a few like hotspots in that map which like looked like they kind of stood out, like the Cygnus region, for example. Would you say this is sort of premature to actually assign those as statistically significant?
Yeah, so you're thinking about like this sort of stuff here, right?
Yeah.
So this analysis was done with a single template, and we extract one number, which is how high the template goes and the total significance. And now we have done all of this analysis that split that into pieces and look at these subcomponents, and those will be presented this summer, and I cannot tell you what the answer is for
Sure.
those things.
No worries. Thanks.
Any questions from this room or online? You're right.
Yeah, thanks for the. I wanted to ask about the splitting in the different eigenstates. So does your constraint depend if it's splitting is different, or are we assuming like all the splitting for all the eigenstates is the same number?
Yeah, that's a good question. So essentially, when I do this analysis on the left, when I have a single delta time square, I'm assuming that all the splittings are the same. And so that makes all of the flavors disappear in a correlated fashion. Now, I can also make the splittings different. So in the figure on the right, I may have one splitting between the first mass states, and then I, for example, just to make the parameters less, the other two splittings be the same. And so when you do that, what happens is you get then these appearances that are flavor dependent. So on the left, you do not affect the flavor composition, but you affect the energy distribution. But when you do the different delta m square, you get both a flavor effect and then an energy effect. In other words to say it, if you change the delta m square differently, you can make more complicated shapes. But we didn't find that when doing that, you get much more significance than just doing it all of them together. And that's mostly due to statistics and whatnot. But it's possible.
I see, and I guess you expect them to be of the same order, right? From the model side, I guess. Like the splittings. Order of magnitude.
Yeah, if they are like, if you think this rectangular neutrino mass is maybe due to some Latin number breaking mechanism that produces all of them, right? So you probably produce them to be of similar scale.
So I guess to follow up on that, it means that there is some sensitivity to the mixing angles in principle.
There is some
If you can
sensitivity.
distinguish flavor dependence.
Yeah, there is some sensitivity to the I mean, yes, the mixing angles start entering when these mass coefficients are different. Yes, they start impacting you. That's right. And I think that what we really are trying to do, so our next generation analysis is really going to target. So if you see this figure on the left, on the right, we are statistically limited, and on the left, lower energies, we are actually systematically limited. And so we are trying to push improved measurements on the lower energies part of the spectrum, and that's going to tell us what's going on with these different flavors and whatnot.
Any other question?
Maybe one brief question. So you mentioned that KM3net event, and that there are two possible explanations. Can you comment on them briefly once more? So I think it was. Yes.
Yeah. So so this image here. So when they came to net, did their analysis, one of their first analysis, they assume what they computed what is the flux that is associated to their to that event, given that the detector acceptance, and that would be the black cross here. However, that is not the correct calculation if you assume that your flux is isotropic. If your flux is isotropic, you have to take into account that other telescopes that are looking elsewhere have not seen anything. And so that gives you the lower flux measurements, which is the blue one. So the sort of bluish. So one way in which you can produce an isotropic emission of neutrinos at high energies is through collisions of cosmic rays with CMB and whatnot. So these are called cosmological neutrinos, and that could well be the bluish cross. You could also have sources that are producing these ultra high neutrinos, and there did a couple of studies looking for sources in that direction. They didn't find any correlation for any source, and I don't have right now the names of the sources. There is another thing that I find very curious when I look at this figure. So you can see the IceCube data sort of goes in a slant, and here we have drawn these sort of dotted lines as to extrapolate it. That blue cross here, the CPPC one, doesn't know anything about the data points to the left. And so the fact that those are sort of continuing, maybe hinting that whatever sources are making it on the left that keep going. It could also be that sources just end, and then the second population happens to have the right order of magnitudes. Unfortunately, all of these questions are open, and I cannot tell you what the answer is. I think we have to. It also, okay, let's say that the flux is, I'm just going to speculate, so let's say that this is a cosmological neutrino, so it's produced by cosmic rays. Well, that would be very bad news, because you can see here in dotted lines the Oyer and IceCube constraints on cosmological neutrinos. That should be lower than these dotted lines. And that makes the cosmological neutrino flux quite small, which means that, current detectors will probably not see another event like this. and you will need to like be larger detectors. So, and unfortunately, I don't think I have that figure in my backups.
So you have future detectors like Trident or those bigger
Yeah.
or Tambo. How far can they go down?
Yeah, I hope I'm sure if I have that. Let's see, this is galactic sources. This is, for example, some models of the cosmogenic that try to replicate these events. And the cosmogenic can produce this sort of level of fluxes if it's down here. I'm not sure if I had the sensitivity of, let's see. Well, in my figure with Tambo, where is that? Where is that figure? Yeah, so the radio detectors are not shown here, which are to the right. But I think there are some experiments that can definitely get to 10 to the minus 9 at these energies, and most of them are radio arrays to get at the possibility. I think with Tambo it's becoming kind of difficult there because you have to have so many detectors. I'm sorry, I don't have the figure that has all of them simultaneously.
Yeah, no problem. Yeah. Thanks a lot. But basically, so Grande also kind of those radio detectors they could go.
Yeah, the radio, but
because they're just much bigger.
You have to be a little careful because those detectors, they are much bigger. However, they tend to be much more efficient, somewhere around like 10 to the 10 GBs, and their efficiency sort of rises up quite fast when they get to like 10 to the 10 to the 9. So it depends a lot in the shape of the cosmogenic neutrino flux. And so I think I had here, where's the cosmogenic? So if the cosmogenic neutrino flux here in there's these shapes here are some cosmogenic neutrino possibilities. So it depends where it peaks, right? So if it peaks at relatively like 10 to the 8, 10 to the 9, then the radios are not that effective. So what the radio community is trying to do these days is trying to lower their threshold so they can move as low as possible. My understanding is that the composition measurements from Oyer favor a flux that is in this sort of 10 to the 8, 10 to the 9 sort of bump area rather than ultra high. So that also motivates, lowering threshold.
Okay, thanks a lot.
Any other question? Online? No? Well, if not,